Okay, so I think we'll get started again. Welcome back to part 2 of the course. We'll continue on with our discussion of sensitivity analysis. This will probably take us at least halfway through our remaining time, and then we'll allocate the remainder to analogs with time-to-event data, mediation analysis, and also the issue of multiple mediators. So we went through the basic approach for sensitivity analysis for unmeasured confounding for total effects on the risk ratio scale. And we touched on this topic at the very end, but we'll discuss it briefly again with regard to how do we really do this in actual practice. And the objection is sometimes raised to sensitivity analysis that it's really too subjective, that an investigator just sort of picks parameters to make the estimate look good and then says, voila, see, my effect's robust after all. And so this is really too subjective to be useful. And I think it's a reasonable objection and one that needs to be taken seriously, but I think there are ways to try to address it and to try to ground a sensitivity analysis more objectively. And so what we have here are sort of 4 different ways to attempt to do this, to remove at least some of the subjectivity of sensitivity analysis. So one approach is just to sort of present how strong a confounder would have to be to completely explain away an effect. Then you're not choosing parameters to make your effect estimate look good. You're simply reporting how much confounding is needed to wipe away the effect entirely. And so that's one way to try to ground the sensitivity analysis more objectively, and then the reader can decide whether they think that amount of confounding is plausible or not. A second approach would be to identify the most important measured confounder, sort of go through the confounders one by one, omit them one by one, and figure out which one shifts the estimate the most. You can then sort of identify what the sensitivity analysis parameters are for that measured confounder. And then you can ask the question, well, let's suppose I have an unmeasured confounder with the same parameters, sort of with the same strength of confounding as my strongest unmeasured confounder. Would that then shift the estimate down to 0, or shift the confidence interval down to 0? If not, then you can at least claim, well, for an unmeasured confounder, to explain away my effect estimate, it would have to be stronger than the most important measured confounder I have. And sometimes that sort of argument can be quite persuasive. Of course, how persuasive it is depends on how well the initial confounding control is. If you've controlled for just about everything, it might be very persuasive. If it's just 1 or 2 not very well measured confounders, that sort of argument is going to be less persuasive. But again, this can be another way to try to more objectively ground a sensitivity analysis. A third approach might be to sort of create a large table with many values. You could have along one axis the effect of the unmeasured confounder on the outcome, on the other the prevalences of the unmeasured confounder and the exposed and unexposed, and make those effects larger and larger and larger as you go across the table, and then just report a whole range of corrected estimates. And let the reader decide what they think is reasonable or not. I think for this sort of approach to be persuasive, you do need to include values which you yourself consider far too large to be implausible, because likely some other reader may disagree with you on the point. So I'd say sort of include parameters up to maybe a 5-fold increase, really strong confounding. Some of those are probably going to explain away your effect, but you can at least get some sense as to how strong the confounding would be to explain it away and what more reasonable estimates might be. And the fourth, and not entirely unproblematic, but the fourth way to try to make the sensitivity analysis more objective would be to try to use external data or possibly expert opinion to inform the parameters. Sort of interestingly, the first 3 of these approaches really don't require you to even know what the unmeasured confounder is to employ these. You can report how large the effects of the confounder would have to be to completely explain away the effect, or its relation to the most important unmeasured confounder. You can do a large table, even if you haven't identified sort of a specific variable that you are missing. If you do have something specific in mind, then the fourth approach can be used as well. But the first 3 don't even require you to know what that unmeasured confounder is. my own view is really this should become routine practice in just about any study with observational data in epidemiology and the social sciences. Epidemiology specifically often comes under critique for one day reporting the results of some food item are beneficial, and sort of a week later that it's detrimental, it's harmful. And some of it's arguably sort of media reporting practices, but I do think some of it is not adequately assessing how robust the results are. And I think if this sort of sensitivity analysis were to become standard practice, I think we'd have a much better sense as to how strong our evidence really is, when we should be making strong claims and when we need to be more cautious. So my own view is this should, again, be part of just about any analysis of, should be included in just about any analysis with observational data. And it can be done in a very straightforward way, even in a sort of clinical journal. At the very least, you can just sort of report how much confounding is required to explain away the estimate completely, how much confounding is required to reduce the confidence interval to include 0. I think those two pieces of information alone provide the reader with a great deal of information. And it doesn't take much text. You can sort of give one sentence in the method section, one sentence in the results, and that's it. If you're publishing in an epidemiologic journal, I think they'd often be happy to see a big table with lots of different values. Might be more difficult with the clinical literature, but again, even with the clinical literature, I think a couple of sentences on this is almost always warranted. And I think the ultimate result of our science and the solidity with which we're drawing our conclusions, I think, would be improved if this were done more routinely. Any questions on this? Yes?
So you're saying the degree of confounding, but there's different parameters here, right? There's gamma, and then there's the proportions, the different proportions of membership in the different exposure groups. And so there's different combinations of those parameters that will explain away the effect.
Yeah, that is correct. There are different combinations of the parameters that could explain away the effect. I think what's often easiest to report is setting those two to be equal. So the effect on the ratio scale, the effect of the unmeasured confounder on the outcome, and the relationship between the prevalence of the unmeasured confounder and the exposure. So is that twofold increase, threefold increase in prevalence, fourfold increase in prevalence, twofold increase in the effect of the unmeasured confounder on the outcome, threefold, fourfold, and just start increasing both of them to sort of equal magnitudes and figure out where that where the effect estimate drops down to 0. That's not the only combination, but that's sort of the easiest to report. Again, how you report, I think, is going to depend a lot on the audience and the context, but I think that's sort of the simplest type of reporting. Yeah, good question. Okay, so pretty much the same thing can be done on the difference scale. We've been talking about the ratio scale, but the results on the difference scale really are quite analogous. On the difference scale, our bias factor is just the difference between our estimate having controlled only for the measured covariate C versus the true causal effect. So we're taking the difference rather than the ratio of those two. And in fact, on the difference scale, the results even more straightforward. So if we're willing to, once again, assume a binary unmeasured confounder, it turns out we can relax this, but if we're willing to assume a binary unmeasured confounder, and the effect of U on the outcomes, the same for the exposed and unexposed, in other words, no interaction between U and the exposure on the additive scale, then the bias factor is just given by the product of two parameters. The first is again, we'll call gamma, which is just the effect of U on Y on the difference scale. Once again, having already controlled for all the measured covariates. That's our first parameter. And our second parameter, which we'll call delta, is just the difference in prevalences of the unmeasured confounder comparing the exposed and the unexposed. So with the ratio approach, we had to specify both of those prevalences. On the difference scale, we only need to specify the difference of those two prevalences of the unmeasured confounder amongst the exposed and the unexposed. and the product of those two parameters gives us our bias factor. Once we've specified those parameters, calculated the bias factor, we can get a corrected estimate and a corrected confidence interval under these simplifying assumptions by just subtracting that bias factor from our estimate and both limits of the confidence interval. That'll give us a corrected estimate and corrected confidence interval. So again, fairly straightforward to do in practice. This is assuming that the analysis has been conducted within strata of the covariate C, as would often be the case. Say if we fit a regression model, if we want to average over those covariates, we can do that and average over the bias factor as well. I think I'm not going to spend too much time on this example here, just to keep things moving. The principles for sensitivity analysis are pretty much the same. It's just that we're specifying the difference in the prevalence and the effect on the difference scale rather than the ratio scale. But importantly, and I've said this a couple of times, all of these are effects that we're specifying, these parameters that we're specifying are conditional on the measured covariate. So it's the effect of the unmeasured confounder on the outcome not having been captured by the covariate. So in this example, if you want to read through it more fully, they have controlled for sort of just about everything under the sun, 74 demographic, clinical covariates. Hard to see what they had missed. And for something to explain away the effect here, it would require really quite substantial confounding above and beyond the measured covariates that had already been controlled for. That's just an interpretative point. This result on the difference scale can be applied irrespective of how the initial estimation was done. It applies if we use regression analysis to begin with, but it also applies if we would use propensity score modeling or weighting or doubly robust methods. Doesn't matter how the initial estimate was obtained, the result is still applicable. Essentially, the only assumption we're making to apply this result is that there's no interaction between U and the exposure on the difference scale, that the effect of U on the outcome is the same for both the exposed and the unexposed. We can even drop the assumption that U is binary on the difference scale. If we have U is not binary, then we just replace our delta parameter, the difference in prevalences, by the difference in expectation of U amongst the exposed and the unexposed. So really the only assumption we're making when we make use of this technique is no interaction between U and the exposure on the outcome. It turns out we can skip over some of this. It turns out we can relax that assumption as well, but then the formulas become more complicated. We have to specify more parameters that sort of more difficult to implement. So there's a little bit of tension between, on the one hand, making some assumptions about the sensitivity analysis to try to get easy to use expressions versus not making any assumptions at all, but then getting techniques which are more difficult to implement and also more difficult to interpret because we have to specify more parameters. Again, this is more of an art than a science, and so I think using the simplified techniques under the slightly simplifying assumptions is a basic way to just get some handle on how robust conclusions actually are. Any further questions about this? Okay, so on we go to direct and indirect effects. And at least the first part of this discussion will be pretty similar to what we saw for total effects. It's going to be, we're going to define the parameters in similar ways. The mechanics are going to look very much the same. There's just going to be one subtlety, and that's going to be the interpretation of the parameters we define for sensitivity analysis are going to be a little bit more difficult to think about. And we'll illustrate that through some examples. But the setting we'll be beginning with is an unmeasured confounder now. We'll begin with the controlled direct effect of the exposure on the outcome, not through the mediator. And we'll ask, to what extent would an unmeasured mediator outcome confounder bias those effects? And to what extent are our estimates robust to such confounding? So we're going to assume that, once again, if we had controlled for C and U, we would have controlled for exposure outcome confounding and mediator outcome confounding, but we don't have data on U, only C. We would typically proceed to estimate the controlled direct effects by simply fitting a logistic regression model, for example. The outcome on the exposure mediator, we could include an interaction term. Our formula for the controlled direct effect before was just e to the theta 1 plus theta 3 m. So our formula would be, if we fixed m to 0, e to the theta 1. If we fixed m to 1, e to the theta 1 plus theta 3. But these will be biased if we have an unmeasured mediator outcome confounder. So as before, we're going to let our bias factor b just be the ratio between the estimate we obtained from the observed data and what we would have obtained had we adjusted for u as well. Bias factor is, once again, difference between the ratio between the estimate and the truth. Just as we did for total effects, we're going to make a simplifying assumption to get an easy-to-use formula. We'll assume that u is binary and has a constant effect, gamma, on the outcome across exposure groups. So once again, no interaction between u and the exposure on the risk ratio scale. So our gamma parameter is going to be the effect of u on the outcome conditional on exposure, the covariates, and the mediator. And we might specify different gammas for different levels of the mediator, depending on which controlled direct effect we're looking at. Are we looking at the controlled direct effect where we fix m to 0, or are we looking at the controlled direct effect where we fix m to 1, or some other level? So we can specify different values for gamma for different controlled direct effects. So we're conditioning on covariate C. We're also conditioning now on m in defining this parameter. So in other words, we're essentially picking up the effect of u on y on the risk ratio scale, not through m. We're conditioning on m as well. So essentially the effect corresponding to sort of this arrow here from u to y directly. That's what we're specifying as one of our parameters. And we can show under these simplifying assumptions that our bias factor for the controlled direct effect is just equal to this expression here, pretty much the same thing we had before, but now these prevalences, this pi 1m and this pi 0m, are the prevalences of u amongst the exposed and unexposed respectively, but now the exposed and unexposed with mediator level little m. And so this is the part which makes the interpretation a little bit trickier, because we're sort of saying, okay, we know u affects m and y, A is also affecting m, and we're going to look at those with a particular value of the mediator. Let's say we're calculating the controlled direct effect for when the mediator is present. The parameters we're specifying then are the prevalence of u when the mediator is present, comparing the exposed and unexposed. And so that can be a little bit difficult to specify. We'll go through some examples to see how we might gain some intuition, but the basic idea is if we're calculating the controlled direct effect, for m is 1, that might be because of u, that might be because of a. If a is absent, then maybe u is more likely to be the cause of m, so we might want to specify a higher prevalence, but we have to do that sort of reasoning on, we're looking at the controlled direct effect with the mediator present. What's the prevalence of u comparing the exposed with the mediator present versus the unexposed with the mediator present? It can be a little tricky. We'll go through some examples to try to gain some intuition as to how to go about doing this. But once we've done so, once we've specified the parameters, the rest works exactly the same way. We've specified the parameters, we calculate the bias factor, we can get corrected estimates and confidence intervals just by taking our observed estimate and our observed confidence interval and dividing all of those by the bias factor. So the mechanics are the same. The parameters look very similar. The one twist, again, is we're conditioning on m in all of the definitions of the parameters. It's not too difficult to think about that for the effect of u on y, but it is a little tricky when we're specifying these prevalences for u amongst the exposed and the unexposed, conditional on having a specific value of m. So let's walk through an example, and as our example, let's return to that birth weight paradox. And as discussed at the beginning of the course, the odds ratio for infant mortality, the odds of infant mortality amongst infants less than 2,000 grams is 0.79 times lower for smoking mothers than non-smoking mothers. So we get this paradoxical, seemingly protective effect. We thought maybe this is due to unmeasured mediator outcome confounding. Maybe something like birth defect, malnutrition would affect both. So we can ask how much confounding would be needed for this explanation to be plausible. And we can just sort of play around with the parameters and see how much would be needed to explain away the estimate. If we do so, and if we specify the effect of U of birth defect or malnutrition on infant mortality as a 3.5-fold increase in the risk of infant mortality. And if we specify the prevalence of U, our unmeasured confounder, birth defect or malnutrition, for low birth weight infants whose mothers smoke as relatively low, maybe just 2.5%, because if the mothers smoke, quite probably smoking was the cause of low birth weight. We don't really need to appeal to any other explanation. So we might specify that prevalence as relatively low. But then if we turn to the low birth weight infants whose mothers do not smoke, we might specify that prevalence of U as somewhat higher, because the infant's low birth weight, the mother didn't smoke, so we know that smoking couldn't have been the cause of low birth weight, so it must have been something else. That might render the explanation that U was present, malnutrition, birth defect, or something else, more plausible. So we might then specify a prevalence of U amongst the unexposed, the non-smoking mothers who have a low birth weight infant, somewhat higher, maybe say 14%, because again, smoking is ruled out as an explanation for low birth weight for the non-smoking mothers. If these were the sensitivity analysis parameters, plugged those in, 3.5, 2.5%, 14%, we'd get a bias factor of 0.79. If we divide our estimate by the bias factor, that would suffice to completely explain away the birth weight paradox. So we don't know what value these parameters actually take are, but what we can say is this amount of unmeasured confounding, mediator outcome confounding, would suffice to completely explain away the birth weight paradox. Doesn't mean it is the explanation of the birth weight paradox, but it suggests that it could be. And if you actually look at the literature on some of these parameters, these are the effects are probably, in fact, higher. So this amount of unmeasured confounding would suffice. But of course, we could play around with the sensitivity analysis parameters and see how the estimate, the corrected estimate, would change under different specifications. Let's look at a second fairly similar example. This was a study published in 2011 looking at 122,000 mother-infant pairs in the South Carolina Medicaid program between 1996 and 2000, and looking at associations between pre-eclampsia, taken as the exposure, cerebral palsy for the infant taken as the outcome, and they did this analysis stratified by preterm birth status. So again, this is sort of like getting at the direct effect of pre-eclampsia on cerebral palsy, not through preterm birth, for preterm infants and for full-term infants. And when they did this, the odds ratios comparing preeclampsia versus no preeclampsia were 0.73 for preterm infants. It looked like there was perhaps a protective effect, and 3.4 for term infants. And here, there were actual potential scientific explanations for why one might have a protective effect of preeclampsia on cerebral palsy in the presence of preterm birth. So maybe this protective effect is real, but it could also, once again, be due to a common cause of our intermediate and outcome, a common cause of preterm birth and cerebral palsy. Something like intrauterine infection, for example, might well affect both. Control for that wasn't made. So we can once again go through a similar exercise. If we specified the prevalence of U for preterm infants. If we start with preterm infants, so we've got two different controlled direct effects. So we start with our preterm infants, where the mediator is 1, the intermediate is 1. We're looking at preterm infants. If we specified a prevalence of U for preterm infants with preeclampsia is relatively low, maybe just 5%. That might be reasonable because preeclampsia is often an indication for preterm birth. Often preterm birth is even induced in cases of preeclampsia to protect the infant. So we really don't need to appeal to any other explanation for the preterm birth if preeclampsia is present. So we might specify a prevalence of U fairly small in that scenario. But if we specified prevalence of U much higher for preterm infants when preeclampsia is absent, because if preeclampsia is not present, that's not the explanation for preterm birth. Must have been something else, so we might specify a much higher prevalence, maybe 50%. Then if we specified the effect of U on cerebral palsy to be a twofold increase, and we plug those in our formula here, twofold, 5%, 50%. What we would get out is a bias factor of 0.7, corrected estimate, and corrected confidence interval. We would divide our actual estimate and confidence interval by 0.7 to get a corrected estimate and confidence interval of 1.04, confidence interval 0.6 to 1.8. If we increase the effect size of U on cerebral palsy to be a fourfold increase, our bias factor would go down to 0.46 when we divide our actual estimate and confidence interval by that bias factor of 0.46. The direct effect estimate increases to 1.6. But even under the more moderate confounding scenario, we would still have a seemingly perhaps very slight detrimental rather than protective effect. And we could go through similar arguments for the direct effect for term infants, which ends up in this example suggesting that 3.6 might be an exaggerated estimate. The actual effect might be somewhat smaller, but it would take very substantial confounding to really explain that odds ratio of 3.4 away completely. So we seem to have pretty good evidence for a detrimental direct effect for term infants, and possibly due to unmeasured confounding, maybe an actual direct effect for detrimental direct effect for preterm infants as well, sort of contrary to what the initial estimates suggested. So again, this is just an example to sort of show the reasoning with regard to how this works and how to get some sense as to whether our effects are robust or not, or whether they might even be in the opposite direction of our initial estimates. Another interesting feature of this example is what happens if we just ignore all of this and proceed with the difference method, and we don't think about interaction, don't think about confounding here. So we've discussed two potential issues with the difference method. One is the possibility of interaction, and then secondly, possibility of unmeasured confounding. And both do seem to be present here. We have potential unmeasured confounding, something like intrauterine infection, and there was certainly some initial evidence, at least, of heterogeneity. The effects seem to be in sort of opposite directions for the two groups. And here, these two issues sort of combine in a somewhat bizarre way if we just proceed with a naive analysis using the difference method, ignoring confounding and potential interaction. This turns out to be one of those scenarios where we've got a positive effect in one group, a detrimental effect in the other, and if we ignore that heterogeneity and just put the mediator, preterm birth, in the model, the coefficient for the exposure, sure enough, reduces to something pretty close to 0, odds ratio of something like 1.1 combined. The conclusion of that standard approach would then be, oh, all of the effect must be mediated. We've put the mediator in the model, coefficient for the exposures dropped to 0, all of the effect must be mediated. And that's precisely the opposite of what our more reasoned approach, allowing for the interaction and trying to take some account of potential unmeasured confounding, led us to which was strong evidence for a direct effect for term infants, and perhaps some evidence of a direct effect due to the unmeasured confounding, which the unmeasured confounding obscured, perhaps some direct effect for the preterm infants as well. So here, these two issues, unmeasured confounding and potential heterogeneity, sort of combine to lead us precisely to the wrong conclusion. This sort of thing certainly doesn't always happen, but it can. And so it's good to be aware of these issues. Again, in any analysis, at least examine whether there might be interaction. Plenty of times it really doesn't matter, but sometimes it does. And confounding is almost always an issue in any of these analyses. So some sort of basic sensitivity analysis is going to be quite important. Any questions on these examples? And where I've seen sort of the most problematic and paradoxical results arise are often when there's sort of a relatively uncommon event, an event that needs explaining, something like preterm birth, something like low birth weight, which is affected by the exposure, but potentially also affected by the unmeasured confounder. Often the direct effect in the strata, which constitutes the majority of the population, the term infants or the non-low birth weight, often the biases aren't too substantial there, but looking at that strata that needs explaining, that has the event that needs explaining, preterm birth or low birth weight, that's where a lot of these strange associations, paradoxical associations, I think often arise and need to be thought about carefully. Okay, we won't spend too much time on this to just keep moving, but similar principles once again apply on the difference scale as well. Everything pretty much carries through from before. On the difference scale, we define the bias factor as the difference between our estimate of the controlled direct effect and the true controlled direct effect, what we would have obtained had we controlled for U also. It's the same bias, same sensitivity analysis parameters, the effect of U on the outcome, not through M, but now on the difference scale rather than the ratio scale. That's our gamma. And our delta is just the difference in those two prevalences of U comparing the exposed and the unexposed, but once again within strata of M. But once we've specified those, the bias factor is just the product of those two, and we can once again get a corrected estimate in confidence interval by subtracting from our observed estimate the bias factor. And from both limits of the confidence interval, we subtract once again the bias factor. So the mechanics work pretty much the same as before. Okay, so that kind of takes care of our discussion of controlled direct effects. Again, the methods look very similar to what we saw for total effects. We just need to be a bit careful in the interpretation of those parameters because they're now conditional on M. We'll spend a little bit of time now talking about natural direct and indirect effects, but this is really an area where there's more methodologic development needed. I'll go through sort of the existing techniques, and there are some scenarios which we can handle pretty well, but not all yet. So try to give a brief overview of what's currently available. So in terms of techniques which are sort of relatively easy to use and implement, there are three scenarios which are covered pretty well, and we'll spend a bit of time on each of these three. One is if there's no exposure-mediator interaction, then our controlled direct effects and natural direct effects are going to essentially coincide, and so that's going to allow us to basically just use the controlled direct effect technique. So that'll be pretty straightforward. Second setting is May and colleagues developed an approach for natural direct and indirect effects, which I think works pretty well, which can be implemented in a fairly straightforward way with their R program. The interpretation of the parameters is again a little tricky, but and sort of hard to specify a priori, as we'll see. But I think this is sort of the best we have right now, because this can be employed in the context of exposure-mediator interaction as well. And then a third technique we'll go through is when the mediator and the outcome are binary, are both binary, we can use an approach pretty similar to what we've described for sensitivity analysis for natural direct and indirect effects, even in the presence of interaction. Okay, so let's begin with the simplest context, which is no exposure mediator interaction. When we have no exposure mediator interaction, the formulas for the natural direct effect and the controlled direct effect coincide. And so what we can do is we can just use our bias factor for the controlled direct effect and apply that to the natural direct effect in its confidence interval, because the two coincide. What we can then do for the indirect effect is as follows. If all we have is unmeasured mediator outcome confounding, then that's going to bias the estimates of the direct and indirect effects, but it's not going to bias the estimate of the total effect, because it's not a confounder for the effect of the exposure on the outcome. And so our total effect estimate is going to be unbiased. And we can sort of use that property to get a very easy sensitivity analysis technique for the natural indirect effect, which is because the total effect's unbiased, the bias for the natural indirect effect is going to be equal and opposite in magnitude to that for the natural direct effect. So whereas we would subtract that bias factor for the controlled direct effect, which is also applicable to the natural direct effect, we would subtract that bias factor from the natural direct effect. We simply add it, that same bias factor, to the natural indirect effect, the mediated effect, to get a corrected estimate. We could do that for the confidence interval as well. So again, this would be reasonably straightforward to do. But that approach is only applicable if we have no exposure mediator interaction. If we do have interaction, this approach developed by May and colleagues can be used. And they've provided an implementation for this in their R package. And so basically how this technique works is we fit models for the outcome just on the exposure, that's sort of our total effect regression, and then our mediator regression and our outcome regression allowing for exposure mediator interaction. And unmeasured confounding of the mediator and the outcome effectively induces correlation between the error terms in the mediator and the outcome regression, E2 and E3. And it may show that if we specify the correlation between the error terms, E2 and E3, in our mediator and outcome regression as rho, that's our sensitivity analysis parameter, just one sensitivity analysis parameter, then the natural indirect effect is just given by this expression here, where everything else can be estimated from the observed data. Sigma 1 is just the variance of the error term amongst the exposed in this first regression. Sigma 2 is the variance of the error term in the second regression amongst the exposed, and this rho tilde is the covariance between E1 and E2 amongst the exposed. Beta 1 can likewise be estimated in an unbiased manner from this regression model. So we can estimate everything except rho itself. We specify rho, we can calculate the natural indirect effects, and then go on to calculate the natural direct effects. So this approach can work reasonably well. They have software to do this. The tricky thing is specifying and interpreting what that rho is exactly. It's a little bit more intuitive to think about the magnitude of the effect of our unmeasured confounder on the outcome. How large is that on the ratio scale or on a different scale? Now we have to specify correlations between unobserved error terms. So it can be a little bit tricky to interpret it. But I think this is the best we have at present. But ongoing work's being done to develop better sensitivity analysis techniques for direct and indirect effects, natural direct and indirect effects. So that's the second possible approach. Third possible approach is applicable only if both the outcome and the mediator are binary. If the outcome and the mediator are binary, the formulas we had before, if we had controlled for unmeasured confounding, are given here for the controlled direct effect and natural direct and indirect effects. These are just copied from our second set of lecture notes. But, of course, we're worried about unmeasured mediator outcome confounding and how that might bias these effect estimates. And we can proceed as follows. We have quite a few sensitivity analysis parameters to specify now, but they look pretty similar in form to what we've already seen. The first parameter is what we saw before, the effect of U on the outcome, not through the mediator. That's our gamma parameter. Effect of U on the outcome on the risk ratio scale. Same thing we had before. We're going to assume that's constant over exposure mediator strata. We then have to specify the prevalence of U in each of the exposure by mediator strata. So what's the prevalence of U in the exposures present? The mediator is present, exposure is present, mediator is absent, exposure is absent, mediator is present, and both are absent. So we have to specify all four prevalences now. Essentially, all of the parameters we would need to calculate our bias factor for both of the controlled direct effects. Once we do that, we've got 5 parameters now, our effective U on the outcome and then our prevalence parameters. We can calculate 3 separate bias factors, and we can get corrected estimates of the theta coefficients from our outcome model, the main effect for the exposure, the main effect for the mediator, and the exposure-mediator interaction term. We can get corrected estimates for our theta parameters by just taking our observed estimates and subtracting off different combinations of the bias factors we had calculated. Once we've got those corrected parameters, we can plug them into our formulas for the direct and indirect effects. So this is a little bit more involved. We have to specify the parameters, calculate the bias factors, get corrected estimates for our theta coefficients, and then plug them into the formula. But this will then give us corrected estimates for natural direct and indirect effects. Unfortunately, if we do this, it's still not so straightforward to get corrected standard errors. It can be done using the delta method, but there's no longer any simple relationship about dividing our estimate by a bias factor and the confidence interval by a bias factor to get a corrected estimate. So this ends up being a bit more involved as well. But that's basically where the state of the literature is at present. There's ongoing work in this area. I'm hoping that a few years from now we'll have better techniques, but this is what's currently available. Any questions on this? We will go through a brief example. Okay. So just to illustrate this, this is an example looking at the effect of placental abruption during pregnancy on different perinatal mortality outcomes. Placental abruption increases the likelihood of perinatal mortality by about 15-fold. In this analysis, we looked at 4 different outcomes. One was stillbirth. Second was early neonatal mortality within 7 days, late neonatal mortality 7 to 28 days, and perinatal mortality defined as stillbirth plus early neonatal mortality. The analysis was of all U.S. pregnancies between 95 and 2000 using the National Center for Health Statistics period-linked files, and essentially just using the methods that we've been describing for, in this case, risk ratios using log binomial models. These perinatal mortality outcomes when placental abruption's present is not particularly rare, so log binomial models and risk ratio scale was used here. This first table just gives the direct and indirect effect estimates for each of the 4 outcomes and the total effect, having adjusted for the measured covariates, in this case, maternal age, parity, education, marital status, race, smoking, and hypertension. And what we see is relatively large direct effects for each of the outcomes Still fairly substantial indirect effect risk ratios. Fairly large total effect risk ratios, close to 15-fold again for perinatal mortality, the total effect. And the proportion mediated is given in this column here. Once again, this conversion to the proportion mediated scale on the risk difference scale can be helpful because the direct and indirect effects, as we discussed earlier, are using different baseline risks. So here, for example, with late neonatal mortality, although the risk ratio for the direct effect is larger than the indirect effect, the proportion mediated on the risk difference scale is actually above 50%. And again, that's because the natural indirect effect risk ratio is working with a higher baseline risk. So what it looks like here is, again, substantial, very substantial direct effects, reasonably large indirect effects, possibly slightly less than half of the effects mediated. But we might be worried about unmeasured confounding in this example, as in many others. If we apply that third technique, where we specify the prevalence of U in each of the exposure by mediator strata, we might specify the prevalence of U amongst term infants as pretty low, maybe just 5%, because really nothing's going on with term infants. Nothing really needs explaining. It's where we have preterm infants that things get complicated, because abruption is often a cause of preterm birth. So if we specify the prevalence of U, our unmeasured confounder of preterm birth and perinatal mortality, as not too common, maybe just 10% for preterm deliveries with abruption, because again, abruption is quite likely the cause of preterm birth. We don't need to appeal to any other explanation here. But a prevalence of U much higher for preterm infants without abruption, maybe 50%, because if abruption is not the cause of preterm birth, it must have been something else. We need to appeal to something else, so we specify a higher prevalence for U in that case. If we were to specify those prevalences, and then we were to specify gamma as maybe either a 1.5-fold increase in the likelihood of perinatal mortality under sort of a moderate confounding scenario, or maybe a 6-fold increase in perinatal mortality under a more extreme confounding scenario, it would affect our estimates as follows. Here we have our observed estimates controlling just for the measured covariates, proportion mediated. Here we have our corrected estimates for the natural direct and indirect effects and the corrected proportion mediated under the moderate confounding scenario and then under the extreme confounding scenario, where U increases the likelihood of perinatal mortality by 6-fold rather than just 1.5-fold. Under the moderate confounding scenario, where U increases the likelihood of perinatal mortality by 1.5-fold, the direct effects go up somewhat. The indirect effects go down somewhat, but not much. The proportion mediated drops a little bit, but not much. Not much really seems to happen. If we move to the severe unmeasured confounding scenario, where U increases the likelihood of perinatal mortality by 6-fold, the direct effects increase dramatically from sort of risk ratio of 13 to 21, 5 to 9, 3 to 4, 10 to 17. The indirect effects go down somewhat more, but still not too substantially. The proportion mediated drops somewhat. So if we take a step back and ask, how do we interpret this all? Well, our estimates really do change under the severe confounding scenario, but our qualitative conclusion that most of it's direct, but still substantial proportions indirect, seems pretty robust, even to fairly severe confounding. And you can play around with the numbers, you can change the sensitivity analysis parameters, and pretty much the same thing holds up. So what precisely are these estimates, these risk ratios? We don't really know. There's almost certainly unmeasured confounding. It's hard to get precise estimate. How confident are we in our overall qualitative conclusion that most of the effect is direct, but still a substantial proportion is mediated by preterm birth? Reasonably confident. We can sort of make these parameters pretty large in that qualitative conclusion, mostly direct, but still fairly substantial proportion mediated through preterm birth.
seems to hold up. And I think this is about as good as we can honestly hope for in any mediation analysis, that we've at least got the overall qualitative conclusions correct. Our estimates are pretty much always going to be wrong because there will pretty much always be unmeasured mediator outcome confounding that we haven't controlled for. But what we can hope to do is at least get the qualitative conclusions right. Yes, there's a direct effect, or oh, no, almost none of the effect is mediated, or yes, the mediated effect is quite substantial. But even that, I think, is not something we can always achieve. So this was an example where things worked out pretty well. The example that initially got me into this mediation questions to begin with was looking at the effects of prenatal care on infant mortality and whether that was sort of mediated by the detection of early pregnancy problems for which the appropriate response would be medically induced preterm birth. Tried to do the analysis as carefully as possible. We obtained sort of moderate total effect risk ratio, protective effect, reducing infant mortality by about 20%, odds ratio of 0.8. The mediated effect seemed to be about 20% of that based on our initial estimates. But just a little unmeasured confounding would flip that mediated effect from being protective to harmful. Very small specifications of the parameters would completely reverse our conclusion. And so in that instance, really have to sort of throw up one's hands and say, we really can't draw conclusions about this question from the data at all. And what sensitivity analysis allows us to do is sort of distinguish between these scenarios. Again, when we can be reasonably confident, at least in our qualitative conclusions, versus when we really shouldn't be drawing any conclusions from the data at all. I realize that judgment on mediation analysis in general is perhaps a bit disappointing. We don't get one estimate. We don't do this particularly well. But it's a challenging set of questions we're trying to ask. We're talking about the effects of not just one, but two different variables, and moreover, the effect of one variable on the outcome as mediated through the intermediate. This is challenging to do with observational data. And so I think realistically, the best we can hope for is getting the qualitative conclusions right. Any questions on this? Okay. So that we may have ended there on a slightly more pessimistic note. We'll try to move to perhaps a topic which might suggest that we can at least in some cases draw more reliable conclusions, even if the confounding seems almost intractable. And we will return to that trial of cognitive behavioral therapy where things really went wrong with the traditional approaches and ask, can we do something else that might help us to draw conclusions in this case? And essentially what we're going to do is we're going to develop or discuss a sensitivity analysis approach which uses data from two separate trials, not just one. So we'll spend a little bit of time on this topic. So as a reminder, this was a trial of a randomized cognitive therapy intervention. The effect of depressive symptoms at 3 months was a third of a point reduction in a scale from 0 to 4 in depressive symptoms. But it was also noted at 3 months follow-up that those with the cognitive therapy intervention had higher use of antidepressants, 27 percentage points higher at follow-up. Comparable at baseline, but those with therapy ended up also using antidepressants more. So the question arose, is there a direct effect of the cognitive behavioral therapy intervention on depressive symptoms independent, not through antidepressant use? If so, we'd want to retain the cognitive behavioral components. If not, we should just focus on compliance to antidepressants. If we regress our outcome on the cognitive behavioral treatment and the mediator antidepressant use, again, the coefficient for antidepressant use in that regression is positive. It looks like antidepressant use makes depression worse. Looks like we've got a detrimental mediated effect through antidepressant use. The direct effect's larger than the total effect. get nonsense out. What's going on? Probably, again, mediator outcome confounding here. We've not randomized antidepressant use. And probably those in more difficult situations, loss of loved ones, relational troubles, are going to both have higher levels of depressive symptoms and are more likely to use an antidepressant. So we get the direction of the effect of antidepressant use wrong. And in principle, you could try to use sensitivity analysis techniques of the type we had described before, but we're so far off in our initial estimate, it's not clear how useful those techniques will be. It's not as though we've established a protective mediated effect and we're trying to assess how robust it is. Here we've got the sign of the mediated effect almost certainly wrong. Looks like we've got a detrimental mediated effect rather than a protective effect, and that's because we've got the sign of antidepressant use in the regression incorrect. So it almost seems like we have intractable confounding here. The problem, again, is introduced because we've not randomized antidepressant use in this study. But of course, there have been plenty of other trials that have randomized antidepressant use. So can we in some way make use of those other trials which have randomized antidepressant use to give us some sense as to what the effect of antidepressant use might have been, or perhaps should be, in this trial? And that's going to motivate the following sensitivity analysis. Yep, question.
This was a clarification question, but even if you randomize antidepressants, the question is that those in cognitive behavioral therapy will increase the use of antidepressants down the road. That can potentially mess up the effect of randomization. So we can obviously start there. But
so we'll get to that as sort of a second stage, but if we could actually randomize everything, what we're going to end up doing is splitting the sample and randomizing just the intervention in one sample, half the sample, and randomizing both the intervention and the mediator in the second sample. But we'll get there later. Right now, we're going to do something a bit simpler, and we'll move towards that sort of design. Okay, so we're going to start as follows. We're going to assume initially that we could run two trials, one of which we randomized the exposure, one of which we've randomized the mediator. In our actual study, we've only randomized the exposure, and we're going to use other data from other trials for the effect of the mediator. But to sort of begin our discussion of this technique, let's assume we could have one population, two different trials. We've randomized the exposure in one, half the population, just the mediator in the other. So this technique is going to assume that the exposure itself is randomized and our mediator is binary, so that we can randomize that as well. We're going to assume that our four confounding assumptions hold for some possibly unknown, unmeasured set of factors, W. We don't need to know what they are, we just assume that they do exist. So really all this is doing is making that fourth assumption, that none of the mediator outcome confounders are affected by the exposure. But we don't need data on what those are. We don't even need to know what they are. So that's a relatively weak assumption. We're going to assume that in a second trial of the same population, we've randomized the mediator, so we can get the effect of the mediator on the outcome in our population. And finally, we're going to assume that the mediator doesn't interact with the exposure or the covariates, W, in their effects on the outcome on the additive scale. The exposure can interact with the covariates in their effects on the outcome or their effects on the mediator, but we're going to assume that the mediator doesn't interact with the exposure and the covariates. Okay, so what can we do then? Well, from the first trial where we randomize the exposure, we can get an intent to treat effect of the exposure on the outcome. That's going to be unbiased drive randomization. We can also get the effect of the exposure on the mediator from that same trial. So that can be done in a straightforward way. Under these assumptions here, which are relatively mild compared to what we were looking at before, but under these assumptions here, the natural indirect effect is actually just given by the effect of the exposure on the mediator, which we obtained from the randomized trial, times the effect of the mediator on the outcome. This is sort of just like the product method, but each of the components now we're obtaining from a randomized trial, of the exposure and of the mediator, respectively. For the natural direct effect, we can just take the total effect of the exposure on the outcome, which again we can obtain in an unbiased way because we've randomized the exposure, and we can subtract the natural indirect effect, and that'll give us our natural direct effect. So if we could randomize both the exposure in one trial and the mediator in another trial, and we were willing to make these somewhat milder assumptions, we can get our natural direct and indirect effects from those two trials. In practice, and in the example we were looking at with the SMART trial, we didn't have data on what would happen if we randomized the mediator, if we randomized antidepressant use in that population. But we could look to other studies. We could sort of treat the effect of the mediator, the effect of antidepressant use on the outcome, on depressive symptoms. We could treat that, that gamma parameter, the effect of the mediator on the outcome, antidepressant use on depressive symptoms. We could treat that essentially as a sensitivity analysis parameter, which would then be informed by other trials in the literature. We could sort of look at the trial that had the largest effect, look at the trial that had the smallest effect, vary that parameter, gamma, and see how our conclusions might change. And so we'll try to do this now with that SMART trial. Again, so antidepressant use was not randomized in the SMART trial, but two other trials published in 2003, 2001, with very different populations, as we'll see, ran randomized trials of antidepressant use and measured depressive symptoms on the same scale as was used in the SMART trial, this SCL-20 scale. The Morrow et al. Study looked at the effect of antidepressant use amongst cancer patients. The Cronky et al. Study looked at the effect in primary care patients. After standardizing the measures, the effect size in the Morrow et al. Study amongst cancer patients was relatively small, just a fifth of a standard deviation, essentially in reduction in depressive symptoms. In the Cronky et al. Study, 0.7 reduction in depressive symptoms. So fairly different effects, but again, fairly different populations as well. But we could treat these essentially as kind of limits for our sensitivity analysis. And that's what we'll do in the following slide. Again, if we take a step back and ask, what's really the question of interest? The question of interest is there a direct effect of the cognitive therapy intervention on depressive symptoms, not through antidepressant use? That's really what we want to know. So the direct effect is going to be our principal target here. And so if we sort of begin with maybe a worst case scenario from the perspective of explaining away the direct effect, that would be if the antidepressant had a very large effect. If the antidepressant itself has a large effect, then that probably means the direct effect is going to be smaller. So if we begin sort of with that as a worst case scenario for the direct effect from the Cronky et al. Study, which was the larger effect size, then using our results from before, the natural indirect effects, just the effect of the exposure on the mediator, and in our actual trial, that was a 27 percentage point increase in the likelihood of using an antidepressant. Our effect of the mediator on the outcome was about a 0.7 standard deviation reduction in depressive symptoms. And so that gives us a natural indirect effect of minus 1.88. Confidence interval minus 2.8 to minus 0.09. For the natural direct effect, then, we take our total effect and we subtract our natural direct effect estimate. Total effect from this trial was a third of a standard deviation reduction in depressive symptoms scores. We subtract our estimate of the indirect effect to get an estimate of the direct effect. So here it looks like about half, even in the worst case scenario, about half of the effect looked direct, about half looked mediated. The confidence interval for the direct effect does include 0 under this worst case scenario. If we turn to the best case scenario from the perspective of the direct effect being present and use the smaller effect size from the Marrow et al. Study, we can repeat the same analysis. Effect of the exposure on the mediators, 27 percentage point increase in use of antidepressants. The effect of antidepressants, minus 0.2. Natural indirect effect now is just minus 0.06. The natural direct effect we take by taking the total effect, subtracting our estimate of the natural indirect effect, so minus 0.33, minus our natural indirect effect, gives us a natural direct effect of minus 2.7. There's a typo in the confidence interval. Sorry about that. It should be something like minus 50 to minus 0.06. Confidence interval does exclude 0 here. So in our best case scenario, it looks like the vast majority of the effect is direct. Only a small part is mediated. Once again, we don't really know what the actual direct and indirect effects are. But what we do know is that in sort of a best case scenario, it looks like the majority is direct. In a worst case scenario, it still looks like about half is direct. A lot of uncertainty in that estimate, but from a decision-making perspective, based on these analyses, we probably would not want to abandon the cognitive behavioral components. It's possible those are quite substantial. Even under our worst case scenario, our best estimate, still half of the effect was direct, not through antidepressant use. That conclusion may be wrong. We do have a fair bit of uncertainty here. But in terms of making the jump to, no, we should abandon the cognitive behavioral components and just focus on antidepressant use, that conclusion probably wouldn't be justified based on these analyses. So once again, we don't get a single estimate, we don't get an exact answer, but we can use this sort of approach to reason about decision making and to gain insight into what might be going on here. So if we can do the randomized trial in one population, then we're on pretty strong ground. If we've only randomized the exposure, we can at least use the existing literature to inform our sensitivity analysis parameters using this two-trial approach to gain some insight into the relative magnitude of direct and indirect effects. Any questions on this approach? Okay. We have made some assumptions even here. We've got rid of most of our confounding assumptions by randomizing the exposure in one group and the mediator in another group or another trial, or turning to the literature. But we are essentially assuming that conditional on some unknown set of covariates W, assumptions 1 to 4 hold. We could just define W as all the mediator outcome confounders. The assumption then essentially just becomes none of those are affected by the exposure. That's essentially what we're assuming here. And then we also assume that the mediator didn't interact with the exposure or the covariates in their effects on the outcome. Can allow for interaction between the exposure and the covariates on the mediator, the exposure and covariates on the outcome, but not between the mediator, effect of the mediator, and the exposure or the covariates on the outcome itself. And that's what essentially allowed us to take that single estimate of the effect of the mediator on the outcome from that one trial and sort of extrapolate it to do mediation more generally. So those were the assumptions we made here. Quite a bit weaker than before. We've got rid of most of the confounding assumptions, but we are making assumptions with this approach as well. In the setting where we can actually randomize in the same trial both the exposure and the mediator, we can come up with some very powerful designs that allow us to draw inferences about direct and indirect effects with no assumptions whatsoever. And this is what's sometimes called a parallel design, described in detail by a paper by Kosuke. And here what we do is we take our sample and we split it in two. And in the first half sample, we just randomize the exposure and we measure the mediator and the outcome. And in the second half sample, we randomize both the exposure and the mediator and measure the outcome. We want that first half sample trial where we randomize just the exposure so that we can get at the effect of the exposure on the mediator itself. If we randomize the exposure and the mediator for everyone, we wouldn't have any sense as to the effect of the exposure on the mediator. So that's why we do what we do with the first half sample. And then the second half sample allows us to get at the effects of both the exposure and the mediator together on the outcome. And it turns out that if you're willing to assume no exposure-mediator interaction, the natural direct and indirect effects are identified with no further assumptions whatsoever. If you're not willing to make that assumption, you can obtain bounds for the natural direct and indirect effects without making any assumptions whatsoever, and those bounds are often informative. They often exclude the null of no direct effect or no indirect effect. So we can draw inferences about these natural direct and indirect effects under no assumptions whatsoever using this sort of parallel design. Of course, doing so requires the ability to randomize both the exposure and the mediator, and would sort of require additional steps in terms of consent, having participants agree to being randomized to one arm or the other of this parallel design trial. But when we can implement it, it's a very, very powerful design. The paper also describes a crossover design for cases where we can give the exposure and the mediator, observe the outcome, and essentially start over with the same person, assuming some sort of washout period. It's not going to work with an outcome like mortality, say, but in some cases we might be able to do a design like a crossover design, and once again we can get effect estimates without assumptions about confounding. But I think these crossover designs will often not be terribly feasible. The parallel design, when it can be implemented, is extremely powerful, extremely useful. There have been a couple of implementations of this now in the literature, but it's not so easy to implement in practice. But I think the sensitivity analysis approach using the two trials really is relatively straightforward to implement in any randomized trial, provided that somewhere in the literature there are other studies that have also randomized the mediator. So I think the potential applicability of that approach is quite broad. But these are sort of ways to try to address these confounding issues which plague all mediation analyses, using not just analysis, but sort of a clever design as well. Yes, question? Yeah, so with the parallel design, essentially in the second half sample, we're doing a 2x2 factorial design. And in the first half sample, we're just doing a regular randomized trial of the exposure. And if we have both, that's really what gives us what we need to reason well about mediation. No, because you don't get the effect of the exposure on the mediator then. That's what you're missing without that first half sample. Yes? That's a completely open topic. Yeah, no, it's a good question. So the state of power calculations for mediation analysis is not terribly advanced. There's essentially one paper, Fritz and McKinnon, that everyone cites. They did some simulations using linear regression with some standard effect sizes, and that's what most people turn to. But that doesn't cover cases with binary outcomes. It doesn't cover exposure-mediator interaction cases. It doesn't cover any of these designs. So there's still a lot of work that needs to be done on power calculations for mediation analysis. If you have some sense as to your effect sizes, you can obtain them obtain power calculations by simulation. But there's really not much, as far as I'm aware of, in terms of good software, existing software resources or analytic formula for this. So. I don't know. My guess is not quite. If what you're interested in is the total effect, my guess would be not quite, because you are gaining something from the second half sample. But you would only use this, I think, if questions of mediation were sort of your primary interest. But again, the sensitivity analysis technique using data from other trials could be implemented even in a randomized trial where you've only randomized the exposure. Yes?
So my question is with the sensitivity, but I've noticed it come up a couple times, so I just wanted to ask, like, still think about it. But a few times today we've talked about how stratifying, like, can kind of let you kind of informally see the direct effect or indirect effect. And to what extent do people use that to justify in their grant applications or, like, the presence of mediation, or do you see what I'm saying, kind of indirectly, because a lot of people do stratify and kind of use it to draw conclusions, and it's kind of getting at the issue, but it's not really giving them.
Yeah, so I mean, I think if your analysis for your primary exposure is stratified by something on the pathway, by a potential mediator, not something prior or contemporaneous, but something on the pathway, then under the confounding assumptions, 1 and 2, no exposure outcome or mediator outcome confounding, those are giving you controlled direct effects. So I suppose one possible justification for carrying out a more formal, careful analysis would be presenting those and saying there seems to be evidence for a direct effect. We want to examine this more carefully. So again, under the confounding assumptions, which are strong, those are controlled direct effects. But what sensitivity analysis allows us to do is say, well, to what extent might the actual controlled direct effects be something quite different from what we've estimated?
Just 2 questions. Why can't we have the interaction in the waterfall that we have randomized for the second sample?
So
why can't we have the interaction between exposure and?
They give 2 different sets of results. One is if you're willing to assume no exposure-mediator interaction, then you can identify the natural direct and indirect effects with no further assumptions, no assumptions about confounding. But you're still making an assumption about interaction. They give another set of results, however, which says, okay, let's drop that assumption of no exposure-mediator interaction. Let's allow for that interaction. Then we can't point identify, but we can still get bounds without any assumptions whatsoever. We can get bounds on the direct and indirect effects, and often those will exclude the no.
And the second question relates to her question where you said something about collapsibility of in the binary. So can you explain a little further on that point? It wasn't clear to me how the odds ratio continued to increase.
I mean, you can simulate data, you can work with existing data in randomized trials, but if the outcomes common in a logistic regression of the outcome on the exposure, if you control for baseline covariates, you can do this at home, the exposure coefficient will go up in general as you add covariates to that model. And it's not that one of the odds ratios is right and the other is wrong. It's just that they're all on different scales. The conditional odds ratios are not comparable to marginal odds ratios. Yeah. And that property of odds ratios can sort of throw off the difference method for mediation analysis. Okay. Our final sensitivity analysis topic is going to be measurement error. This came up in our analysis of our example in genetic epidemiology, where average number of cigarettes per day was self-reported, subject to error. So these results here are going to assume that M is subject to non-differential measurement error. So all we observe is a measurement of our mediator, which is equal to the true mediator plus some random error. We might then proceed with fitting a logistic regression model, say for our outcome, using the observed mediator measurement, and maybe a linear regression for our observed mediator measurement on our exposure and covariates. This would sort of be the naive approach. Our mediator regression here for a continuous mediator is actually going to be fine. Our estimates will be consistent for the true betas. It just introduces essentially additional random error into the regression model. But that's not the case with our logistic regression model. The measurement error in the mediator is going to throw off our estimates of the theta coefficients. But what we can do is just use fairly standard, well-established measurement error correction techniques for that logistic regression to get corrected estimate. So we could use, for example, method of moments correction or regression calibration or SIMEX methods to get corrected estimates of theta 1, theta 2, and theta 3, and then use those corrected estimates to get corrected natural, direct, and indirect effects. And to do so, if we sort of pursue more of a sensitivity analysis approach, if we didn't have a gold standard measurement for any subsample, all we need to do, it turns out, is specify a single sensitivity analysis parameter, which we'll call lambda. The proportion of the variance in our mediator measurement that's explained by the true mediator. So our mediator measurements, true mediator plus error. What proportion of the variation in the mediator measurements due to the true mediator, what proportion is due to random error? And that's what proportion of the variance conditional on the exposure and the covariance. But once we specify that one parameter, that's essentially all we need to get corrected estimates. So in some sense, this is almost easier from a conceptual standpoint, at least, than the problem of unmeasured confounding. Is 75% of the variation in our mediator measurement due to the true mediator, or just 50%, or just 25%? We can sort of vary the parameter in a sensitivity analysis. In the absence of exposure-mediator interaction, we actually get pretty easy closed-form solutions to this, and this is, again, just sort of standard measurement error correction results. The corrected theta 1 coefficient in the absence of exposure-mediator interaction is just our estimate of theta 1 minus the estimate of theta 2 divided by our sensitivity analysis parameter lambda times the effect of the mediator, the exposure on the mediator. And to get a corrected estimate for theta 2, we just take our observed estimate of theta 2 divided by lambda. So we can get corrected estimates pretty easily. When we allow for the exposure-mediator interaction, this can still be done, but we no longer get these very simple closed-form expressions. But we have software code to implement these corrections now. No macros yet, but this correction for measurement error can be done. So methods are available which allow for exposure-mediator interaction. Something similar, though it's a little more complicated, can be done if the mediators are binary and subject to measurement error. Another paper looked at differential measurement error and has some results for that in the absence of interaction, at least. So there are a number of measurement error scenarios which have been covered in the literature. We're not going to go through all of these in detail. I think you have a general sense of the flavor as to how these work, and which one to use is going to depend on the specific analysis. But a lot of these still require sort of more specialized software. There's often code available, but no macro to implement. Sort of one other interesting topic from the perspective of the effect of measurement error on mediation analysis is we might sort of think intuitively that if our mediator is subject to measurement error, then that will weaken the mediator outcome association, and that'll sort of bias downwards the indirect or mediated effect, because that mediated effect is essentially the effect of the exposure on the mediator times the effect of the mediator on the outcome. If we've weakened that mediator outcome association, we should sort of underestimate the mediated effect, and therefore we might think we would overestimate the direct effect. So we might ask, when does this hold? And it turns out it holds in many common scenarios, but not all. if the natural direct and indirect effects are in the same directions, and we have non-differential measurement error of the mediator, then that intuitive conclusion will always hold if either the mediator is binary, and it will always hold, or if the mediator's continuous and normally distributed and there's no exposure-mediator interaction in either a linear or logistic regression model. But if the mediator has 3 levels, for example, or if there is an exposure-mediator interaction, the intuition can break down. In most scenarios, it does still hold, but it doesn't always in some of these more obscure settings. But we could still do sensitivity analysis even when the intuition breaks down. But often the intuitive results, perhaps all we really need to know to proceed with reasoning. Okay, so to conclude this bit on measurement error, let's return to our example from genetic epidemiology. We saw that allowing for exposure-mediator interaction in our analyses, our estimates of the natural direct effect odds ratio were 1.32, natural indirect effect odds ratio 1.01, proportion mediated about 5%. Looked like most of the effect was through other pathways, but we were worried here that measurement error in our mediator, self-reported average number of cigarettes per day, might compromise that conclusion. That would weaken the association. Our indirect effect would be an underestimate. The proportion mediated might be substantially larger. So how might measurement error affect these conclusions? If we fit a model for the outcome using the observed mediator measurement, but adjust for measurement error using regression calibration here, if we specify lambda as 50%, in other words, our mediator measurement, 50% is due to true mediator value, 50% is due to error. The natural direct effect goes down somewhat to 1.27. The natural indirect effect goes up a little bit to 1.02. Proportion mediated increases to about 9%, but it still looks like the vast majority of the effect is direct. If we allow for up to 75% error, only 25% of our mediator measurements due to the true cigarettes per day, 75% is due to error. The direct effect actually does go back up here, but the indirect effect increases more substantially. The proportion mediated goes up to about 15%, so quite a bit larger than in our initial estimate of 5%. But our qualitative conclusion that most of the effect seems to be through other pathways still seems to hold. So again, do we know here what proportion is mediated? No. Would we if we had a sample size of 1 million? Still no, because of these issues of measurement error and unmeasured confounding. But having gone through these sensitivity analysis, I think we can be reasonably sure that most of the effect is not mediated by average number of cigarettes per day. Most of the effect is through other pathways. Maybe it's 5% mediated, maybe it's 15, maybe it's even less. We don't really know, but all of the sensitivity analyses seem to suggest that probably not much more than 15, maybe up to 20% of the effects mediated, but the vast majority seems to be through other pathways, not by changing average number of cigarettes per day. Is there a question?
Sorry, go ahead.
These seem to focus on measurement error in the mediator. What about measurement error in the confounders, particularly the confounders between the exposure and the mediator? So you have residual confounding. Would that affect? I understand your intuition about what we expect in terms of the natural direct and indirect effects when there's measurement error in the mediator. So what about intuition?
Yeah, so there's been a little bit of recent work on measurement error in the outcome and in the exposure. With the outcome, the results are pretty nice and pretty intuitive. For a continuous outcome, you actually get unbiased effects, and for a binary outcome, both the direct effect and the indirect effect are biased downwards, biased towards the null, sort of what you would expect. With measurement error in the exposure, it's a little more complicated. In the absence of exposure-mediator interaction, the direct effects always biased towards the null. but the mediated effect can go in either direction. And it really depends on whether the measurement error in the exposure induces more bias in the effect of the exposure in the mediator, which would tend to underestimate that effect, or whether the measurement error in the exposure introduces more bias in the effect of the mediator on the outcome in that regression by having mismeasured the exposure. And so it can go in either direction.
I think a lot of epidemiologists think about measurement error in their exposure and their outcome, but not everybody thinks about residual confounding due to measurement error and confounders. So what I'm thinking of is in your diagram where you had two sets of confounders, one that's between exposure and mediator and the other between mediator and outcome. I don't think the second set matters that much because you already show you need a strong relationship between your mediator and those confounders to even bias the indirect effect. But for that first set between the confounders, so I'm curious about measurement error and the confounders between the exposure and the mediator.
Yeah, so I don't think, as far as I'm aware, there's any literature on measurement error in the confounders for mediation analyses. It's possible there's something in the social science literature. There's sort of a large social science literature on mediation that doesn't put it in a causal framework and assumes everything's linear, but there might be something there, but I'm afraid I don't know. I mean, another way to treat measurement error in the confounders would be as sort of a phenomena of unmeasured confounding, and there are some techniques. Yeah.
It would be interesting in terms of how it affects the mediation, the proportions on either side.
Yeah.
So when you're doing sensitivity analysis, you're suggesting that we should do piece by piece, or can we do it in a single where we are trying to assess the measurement error and we're trying to understand unmeasured confounders, all of them together in one?
So that's going to depend on the context. There's sort of a literature on what's sometimes called multiple bias analysis, and that's been done for total effects in many cases. I'm not sure I can think of an example from the mediation analysis applications. But again, some of it's going to depend on the context. In the example here, it seemed like the unmeasured confounding actually just further supported our conclusion, so we really didn't need to worry too much about that. The measurement error seemed to threaten our conclusion, and so that's really where it perhaps made sense to take a more quantitative approach. But you could imagine examples where both of those biases potentially threaten the conclusion, and then in that setting it might make sense to do a multiple bias analysis for the direct and indirect effects. Again, I'm not aware of any literature on that, but it might make sense in some contexts. Okay, so that brings us to the end of our sensitivity analysis lecture, the third part of the course. We've seen that these techniques can be useful for assessing how much unmeasured confounding is necessary to explain away the effect, or to get some sense as to what plausible range of estimates might be. The techniques are useful for total effects, and I think pretty much should always be used in observational studies. The techniques are also essential for direct and indirect effects. We're making strong confounding assumptions which are almost always violated. And so it's essential to accompany any mediation analysis with a sensitivity analysis as well. Likewise, if we're worried about measurement error, there are techniques available to address that as well. We can do this with controlled direct effects in a reasonably straightforward way, essentially by hand. There are some techniques available for natural direct and indirect effects, but more work still needs to be done on the topic. But that gives you sort of an overview of the literature at present. And really what I would argue is the importance of using these types of techniques when doing mediation analysis. So with that, why don't we take a 15-minute break, come back just a little bit after 3:20. We'll spend maybe a half hour on time to event outcomes. As we'll see, it's going to look exactly the same as what we had before. There's not going to be terribly much new there. The results will extend in a straightforward manner. And then we'll spend the last 45 minutes or so on multiple mediators, where some new challenges do arise. So we'll be back at 3:20 or a little bit after.